Vamos voltar, pessoal, quem estiver lá fora. A gente já vai começar a nossa última palestra, fechar esses 2 dias de muita reflexão, cabeça fervendo, muitas ideias, muito conteúdo bacana. E essa próxima e última palestra do Festival Futuros Possíveis vai tratar sobre um tema de como é possível, o que a gente pode fazer para resolver o problema da escassez de matéria-prima e diminuir os desgastes ambientais que a extração dessas matérias-primas geram. Será que a resposta para esse problema pode estar na mineração de asteroides? Olha só, isso a gente pensa um futuro muito longe, de repente. Então, a partir de agora, eu vou começar a falar inglês para poder convidar ao palco o nosso próximo palestrante. So, I would like to welcome to the stage Mitch Hunter. He's the CEO and founder of the Asteroid Mining Corporation Limited Global. Uma salva de palmas para ele. Que vai falar sobre a mineração de asteroides, solução para a escassez de matéria-prima no planeta? Fiquem com Mitch Hunter. Your microphone.
Thank you very much. Thank you very much for having me here. It's a pleasure to be in Brazil. It's my first time, so thank you so much. So I'm going to talk to you today about asteroid mining and essentially just run you through some technical and commercial considerations of asteroid mining. So just to give you a bit of background, so I'm the CEO and founder of Asteroid Mining Corporation. I founded a company in 2016 in my university bedroom, and I studied international relations and history. And for my international relations dissertation, I realised that I wanted to write on what I thought would be the most disruptive thing in our lifetime. And I settled on asteroid mining because I was looking at the economic opportunity of asteroids, and I was thinking that the Earth's resources are inherently limited, so it would make sense after a certain point to start looking for resources beyond our planet. So at Asteroid Mining Corporation, we do 2 things. So we predominantly focus on robotics. We have a partnership with Tohoku University Space Robotics Laboratory, and we are developing the space-capable Asteroid Robotic Explorer, which is a 6-legged spider robot which can be used on Earth, as well as being capable of delivering payloads in space, crawling down into lunar craters and walking over the surface of asteroids. And then we also do satellite development as well. So we are currently developing the Asteroid Prospecting Satellite 1, which will essentially look for asteroids which can be potentially valuable, and then look to analyse those resources within those asteroids, looking predominantly for precious metals, but also for water as well. And essentially, we are looking to build a map of the solar system, and essentially, we are hunting for treasure in space. So let's start with what asteroid mining is. So asteroid mining is the prospecting, exploration, and extraction of resources from asteroids. There's many use cases for this asteroidal material. The one that we're most interested in is in platinum group metals for hydrogen fuel cells, catalytic converters, electronic devices. In fact, 25% of the global platinum supply just goes into smartphones every year. So everyone who carries a smartphone with them is carrying a small amount of platinum on them. Also, platinum group metals are very useful for things like turbine blades, medical equipment. Platinum is fully biocompatible, so you can use it for implantables into your body. And also, there are many, many other use cases for platinum, particularly in hydrogen catalysis, hydrogen fuel cells, for example. Beyond precious metals, there is also water. So different asteroids have different compositions, as we'll come to in a second. But some asteroids contain water, and the water in the form of ice and hydrated clays on the surface of asteroids can be used essentially for drinking, for oxygen, and also for spacecraft fuel. Beyond this, there's also heavy metals on asteroids as well, which aren't as useful, but for building things in space. So if we want to be building larger space stations in the future, starting to build larger spacecraft in orbit, and also potentially be building on the moon, then we would potentially want a source of heavy metals as well, and asteroids can provide them. So we founded the company with the goal of developing the enabling technology to develop a global market for space resources, and essentially having the data and the tools for anybody with the budget to essentially fund an extraction mission. So we like to consider ourselves as the shovel salesman of the 21st century's gold rush. So where are asteroids? Well, fortunately, there is quite a lot of them. So you've got two main characterizations of asteroids. You've got your main belt asteroids. So there's over 1.5 million, which are over 1 kilometre in diameter, and they rest predominantly between Mars and Jupiter. But the ones that we are more interested in are the near-Earth asteroids. So there are over 30,000 near-Earth asteroids, and they orbit between Venus and Mars, and predominantly follow the Earth around the solar system. The near-Earth asteroids are much easier to get to from an astrodynamics perspective, and some of them are in fact easier to get to than the Moon energetically. So these are the ones that we are most interested in. So let's look at the economic potential of asteroids. So this is a single 1 kilometre diameter, upper 90th percentile, platinum-bearing metallic asteroid. And this is a table which has been done by Liverpool John Moores University Astrophysics Research Institute using meteoric data as the analysis. For this 1 kilometre diameter asteroid, you would be looking at approximately 117,000 tonnes of platinum, whereas on Earth, the entirety of Earth mined 170 tonnes of platinum last year. So you are looking at essentially 688 years worth of global supply within that single asteroid, and that gives, purely on platinum alone, a value of over £3 trillion. If you tally up all the other platinum group metals, and in fact some of them are particularly valuable, so things like osmium, which just doesn't get much production on Earth, on that same asteroid we can reasonably expect to be finding 58,000 tonnes of osmium, and that is over 1 million years worth of global supply. So that is a lot of economic value within the resources within these asteroids. The total value of that 1 kilometre diameter asteroid would be £20 trillion, which is roughly 10 times the gross domestic product of the United Kingdom. So these are tremendously valuable. So space resources are very important in terms of global security because obviously the distribution of resources is not uniform throughout the Earth. So the main countries which produce platinum group metals, in fact, are South Africa, Russia, Zimbabwe, the US and Canada. They make up about 99% of the distribution of platinum. And as global resource competition is increasing, then we're seeing a demand for these non-fuel minerals being required for emerging technology, such as hydrogen vehicles. So this supply is unevenly distributed, but it is also possible for countries like Brazil, like the UK, who do not have their own supplies of platinum group metals, to go and get them in space instead. So asteroids have the opportunity as well through space resources, or space resources have the opportunity through asteroids to allow nations intending to stay at the cutting edge of innovation to have their own steady supply of these key strategic resources for their industries. And this can't be guaranteed using existing terrestrial supply chains, which are vulnerable to geopolitical risk. So, for example, we've got next generation engines, which require platinum group metals. Companies like Embraer, obviously, doing engine development. And then, obviously, you have platinum being biocompatible, means that it is also useful for biotech applications as well. So countries will need to ensure that they have access to these resources going forward, and asteroids provide the opportunity to do that. So space resources are also very valuable for the green transition as well, particularly looking at the Sustainable Development Goals 13 and 7, so climate action and affordable and clean energy. Being able to have a greater supply of platinum means that we can have and we can increase the uptake of hydrogen fuel cells. So the reason why no one is currently driving around in a hydrogen car is because it requires a kilogram of platinum for a hydrogen engine, and that is £25,000 or approximately about $40,000, $35,000. So you essentially, before you build anything off the vehicle beyond that, you already have a very, very high price point. And also we've got for catalytic converters for fossil fuel engines. Having platinum means that we can make fossil fuel engines more efficient as well, where we can ultimately start to make that transition to greener forms of transport. So metals extraction often takes place in the global south under unethical conditions, and there are proposed alternatives to asteroid mining and kind of Earth-based mining, which is seabed mining. And I would argue that seabed mining is incredibly dangerous because we don't really understand the seabed yet. And we often get accused of, well, if we were to find something in space, then I think that we would probably win Nobel Prizes if we were to find something alive in space, whereas we know that things are alive at the bottom of the seabed, so you'd be causing untold ecological damage if you were to start mining the seabed. So being able to go for these low externality resource acquisition is a key prerequisite for sustainable development. And it's been shown through studies that space-based platinum group metals would have an order of magnitude less CO2 equivalent emissions per kilogram than those which are currently extracted from terrestrial mines. So we have a 20-year vision. We focus currently on terrestrial robotics because that allows us to have a platform of profitability. So we are currently developing robots for use in things like shipyards, doing inspections. It's very much the same robot that we'll be sending into space, but using the unique characteristics for space and deploying them to Earth-based markets. Beyond this, we are looking at prospecting with the asteroid prospecting satellites, and these will be a series of space telescope missions to survey and estimate the composition of near-Earth asteroids and main-belt asteroids. And then towards the end of this decade and the beginning of the next decade, we'd be looking at exploration as well, where we'd be sending one of our robots to an asteroid in order to ground-proof the resources within the asteroid and essentially take core samples and prove those resources so that we know that we are essentially justified in going to go and mine that asteroid. We can also look at sending one of our robots to the moon within the next kind of 4 or 5 years as well, in order to explore places like Shackleton Crater, where we know there is water on the seabed. So we have an 8-year roadmap in order to get us to an asteroid. So we are focused on 3 main areas, which are robotics, space, and legal legislation. Because obviously space resources is a new sector, so there's not a huge amount of laws surrounding space mining, and that means that there's some development work which has to be done in the meantime alongside the satellite and robotics work as well. We'd be looking at sending our robot to the moon probably by about 2027, and we'd be looking at sending up our satellite around about 2027 as well, in order to start generating that data set of valuable asteroids. And all this will lead to, by the early 2030s, us being in a position where we can start mining asteroids. So one of the key problems with prospecting asteroids is there's just a lack of data. The data on asteroids right now is quite limited. So we know where some of the asteroids are, but we don't really know what they're made of. A lot of the analysis work is just to see if the asteroids are hazardous, rather than whether or not they might be potentially valuable. So that lack of compositional data is quite challenging, and that will require new satellites being made in order to go and prove those resources are out there. Also, the direct sample analysis is still very early stage, so you have organisations like the Japanese Space Agency and NASA who are capable of landing on asteroids and taking small samples, but this hasn't been done at a commercial grade just yet. And this means that there's a lack of a systematic, structured and comprehensive data set. So what we're currently doing is using ground-based telescopes in order to collect data on asteroids, but the problem is telescopes can only be used at night, and they often have to be on clear, cloudless nights as well. You can't be seeing through clouds. So that means that it's very expensive to be using ground-based telescopes. It's £10,000 per night to use a 2-metre diameter telescope, and it costs £10 million to build one of these telescopes. So to break that figure down, that means that it's about £2,500 per observation of an asteroid, and that's based on 5,000 observations during the lifespan of a telescope. And these telescopes are also very limited to select universities, which mean that the data sets which do currently exist are quite small and also unconsolidated. There's not one universal data set as of yet. But our solution to this problem is to have the Asteroid Prospecting Satellite 1, which will calculate the orbital data, but also establish the composition of these asteroids through compositional analysis, and we'll be taking spectral analyses of these asteroids in order to find out what these asteroids are made of. This will then lead us into identifying candidates for future sampling missions, where we can then go and land on the asteroid and take the resources. And then this allows us to essentially populate a space resources database, which will be a catalogue of the resources of the solar system. By having a space telescope compared to a ground-based telescope, it means that you have a much higher duty cycle. So even though you are limited in the amount of time that you can spend in orbit, because eventually it will fall back to Earth and burn up, based on a 5-year mission duration, you can have a high duty cycle of essentially 24/7, 365 days a year. So you're not limited by clouds, you're not limited by good weather, you're not limited by night. If you put the satellite into a sun-synchronous orbit, then you will have the sun constantly behind you and you'll be pointing out into the solar system. So you'll be capable of seeing where the asteroids are 24/7. This means that we can bring down the cost of getting these analyses. So we can get it down to £2,000, which is still cheaper than building a ground-based telescope. And it means that we can expand the use cases for these observations as well. For example, for space debris monitoring, if there was to be a crash between two spacecraft in orbit, then we could be pointing the satellite in order to analyse potential impacts from that as well. So this is just a very rough outline on the Asteroid Prospecting Satellite 1. So we are developing the optics package in-house. We'd be looking at approximately 2 observations per hour, and it would be in an 800-kilometre sun-synchronous orbit, which means that the sun's constantly behind us. This gives us a 5-year mission duration, which means that we could potentially expand to 9 years if the spacecraft continues to work. And this means that we would be capable of generating several tens of thousands of categorizations of asteroids, which would mean that we would have a much better understanding of the value of these objects. So this is our robot. This is the space-capable Asteroid Robotic Explorer. It's a 6-legged spider robot. It can climb, it can go down into craters on the moon, it can go into caves. Basically, it can go anywhere that you wouldn't want to be sending a human being. So that includes things like earthquakes, into buildings after earthquakes and disasters, and also into the permanently shadowed regions on the moon, which are very cold and quite inhospitable. Even when we're sending rovers to the moon in order to do these explorations, they are quite limited in the fact that they can't go above or below 15-degree slopes. So in order to go down into craters, then we need a climbing robot. So these are our partners at Tohoku University. We're very fortunate to have our Japanese partners. We are working with them now for 2 years. They've previously contributed to the Hayabusa 1 and 2 asteroid sample return probes, and they were also participants in the Google Lunar X Prize as part of the Japanese team Hakuto. Their research interests predominantly include rough terrain mobility and remote planetary exploration, and they are some of the finest experts in the world when it comes to space robotics. So just to go into more detail on the robot, it's a biomimetic design, so it follows what we see in the animal kingdom. We chose a spider because it can climb and it means it can go to those hard to reach areas. So being inspired by a spider for the key structure of the robot, but then also being inspired by reptiles as well, particularly geckos, and the way that their hands can grip allows us to be able to go and climb on rough surfaces. We can also swap out the grippers as well, so we could be, if we were wanting to climb on the outside of a building, for example, then we could put a vacuum pump gripper system, or we could put an electromagnet if you wanted to go up a steel structure. So it's fully symmetrical, fully reversible, there's no such way as up, and it's fully modular, which means that we can swap out payloads for a very versatile mission profile. It's very scalable, so the current robot that we have in Japan is 20 kilograms. But we can scale that up to 200 kilograms, which would be about 5 meters across, which would be very, very big. It's capable of going underwater, also into microgravity and vacuums as well. It's radiation hardened because it's designed for space, so it means it can be used in nuclear sites, for example, and it's also toxin proof, which is obviously very helpful. We've developed all the electronics ourselves. So navigating over this extremely rough terrain on an asteroid is just impossible with a wheeled rover. In order to manoeuvre over the surface of an asteroid, you need to have legs. One of the key lessons that we learned from the mascot lander as part of the Hayabusa program was that in order to do this targeted locomotion and the targeted exploration of interesting sites, then you need to be able to essentially attach yourself to the surface and walk over the surface. So the mascot lander was essentially a robot which was powered by gravity, and it had a tap door. So the tap door would open up and it would go up into a kind of low orbit over the asteroid, and then would come back down to Earth again. Not to Earth, to the asteroid, and that was completely randomized sampling. So in order, if you were wanting to do space resources and you wanted to identify particular sites, then you would need to be able to go in a targeted manner in order to get there. But having a legged climbing platform means that you can go anywhere which has a solid interface. So that means vertical and inverted surfaces as well. So it could climb the walls and could also climb the ceiling too. And the grippers which attach the robot to the ground also mean that it has tactile capabilities as well, so it's capable of feeling the ground, feeling whether or not it's solid, and this allows for more data collection as well. So the navigation of the robot is designed, it's fully autonomous because you have a time delay in space. Asteroids can have time delays of several seconds through to up to 30 seconds, so you can't be controlling it. It needs to be autonomous, and the robot is capable of essentially navigating itself. Also there's no GPS in space as well, so this means that for the robot to localize itself, it needs to be done internally using cameras and depth sensing equipment. And by maneuvering over an area, it allows this data to be compiled, which can build a map of the region which it is exploring as well. So the robots are also swarm compatible, using swarm intelligence. So it's the collective behaviour of self-organised systems. This can be natural or artificial. So for example, birds, when they fly together. What you're seeing here is a team of 6 robots trying to navigate this exploration area in as quick a time as possible, and doing the most efficient path planning in order to do that. So we have multiple operation modes which are fully autonomous, where the robot decides for itself how it will achieve its mission goals. We have semi-autonomous, where we can request the outcome and define some constraints. And then we have remote controlled as well, which would be sufficient for terrestrial applications, but would be impractical for space missions. So our goal is to explore the inner solar system by creating low-cost, high-impact solutions to advanced exploration. SCARY is being designed for both asteroid exploration and terrestrial use cases, but its gravity-agnostic capabilities mean that it can be applied to lunar and Martian exploration as well. So just before I finish, I'd like to talk about some legal considerations of asteroid mining as well. So asteroids are highly dangerous environments for working in. You wouldn't really want to be sending astronauts up there. Debris being created by drilling and mining operations has the capability to destroy spacecraft if it's not properly shielded. So a legal environment has been proposed, which would be, oh, have I missed that? Yeah, that's not going to work. But basically, you would have your landing site, and you would have a priority rights around your landing site. So you would have an exclusionary safety zone, which would mean that you would prevent other operators from coming into that environment, just so that you don't have a position where you have 2 spacecraft essentially competing over the same area. So yeah, that was me. Thank you very much.
Thank you, Mitch. Quem quer fazer pergunta para o Mitch? Só levantar a mão, ó, já tem 1, 2 pessoas. We're opening for questions.
Yep,
So, do you have earphones for?
Oh yes, I'll go over there.
No, they bring it to you. They bring it to you. Que eu também, gente, traduzi física ontem, asteroide, nem deixa, pelo amor de Deus, profissionais para isso, maravilhosos, só trazer o fonezinho para ele. Yesterday I had to translate the questions about physics, but about asteroids I'm not going to try.
Okay.
I'm not capable of doing it.
Actually, I'm going to ask in English, if it's okay.
Yeah.
So a very interesting talk. I'm just curious about, like, if you could elaborate a little bit more about the biosafety issues that you may have in this kind of proposal. how are you going to avoid any kind of contamination with material that you're bringing back to Earth?
Yes, absolutely. So when it comes to the kind of biological safety, it is highly unlikely that there would be anything alive on an asteroid. But before we would be bringing it back for commercial sale, then it would probably be analysed at the International Space Station, and you would take a sample of some of the material which is being recovered, and you would essentially just check to ensure that there is no kind of biological signatures or anything kind of alive on there. If we were, however, to find something alive, we wouldn't then mine that asteroid, but we probably would win Nobel Prizes, so it wouldn't be a bad result.
It will be in English as well.
That's okay.
So are companies like Apple and Samsung, for example, already buying this kind of materials? Are they already using this kind of materials? And when do you see it being viable, like in a main scale?
Yes, so I mean, platinum group metals are widely used terrestrially already. Big corporations are buying up major supplies of it. In order to get a transition to a hydrogen-based economy, or to even just start to decarbonise the economy, then you would need a much, much greater supply of platinum than we currently have. If we are mining approximately 200 tonnes of platinum per year as a planet, that's just not enough to sustain a transition to a hydrogen-based economy, or even to see widespread adoption of hydrogen vehicles. So there will be an inflection point when there is mass market adoption. I couldn't tell you when that would be. I would imagine it would probably be in the early 2030s. But these resources are increasing in scarcity and they are finite, so going and finding new supplies of them will help.
Mais alguém tem pergunta para o Mitch? No? So Mitch, I would like to thank you so much
Thank you.
for coming here.